Hi, I'm Ramsey. I'm from Michigan. I go to the University of Alabama for aerospace engineering. I'm doing an internship with Hydrocraft this summer, doing a bit of foil design, and I'm looking forward to talking a little bit about how the foils and the airfoils actually work. A bit of a beginner. I'm just getting into winging out here now. I've done a good bit of wake foiling, all on stuff that I've home built, hand shaped out of wood and glassed over. And it's been great to get on some real gear out here, and very fun to have a little bit of a hand in designing some of it. So I wanted to start with kind of just a basic overview of the makeup of a foil. So with your foil, we have what we call a plan form. So that'll be your 3D outline. In looking at kind of a projected top-down view of it, you have wingtip to wingtip, your span, and then leading edge to trailing edge is your chord. And then if you look front on, you've got your thickness, and then you have what we call an anhedral or a dihedral. So this gets mixed up a lot. These foils actually have a slight anhedral, which is a downward slope from the root to the tips. And a lot of fighter jets do this, and it helps with maneuverability. Anhedral makes it so that you're kind of wanting to turn. You're not as roll stable, which is usually a good thing if you want to crank turns. And then commercial aircraft will a lot of times have a dihedral, so their tips are actually higher than the root of their planform. And this creates a really, really roll stable planform where it actually, if you roll, it wants to come back to that horizontal, which usually isn't used in foils because it's not the greatest for turning. It's kind of harder to initiate a turn. I wanted to talk about aspect ratio too. So aspect ratio kind of relates your span to the area of your wing. And so a really high span with a really low area wing gives you a very high aspect ratio. Think kind of like your downwind, your race foils. And a higher area or a much lower span will give you a lower aspect ratio, so kind of more of your surf foil. And the higher aspect ratios, since you have a larger span, it can sometimes be harder to initiate a turn, where like your lower span, your surf foils, more of your area is kind of under your feet. And so that can make it a little easier to initiate turns. And that's kind of why you can see here, we have fairly short chord wingtips, and then our root has a pretty nice long chord. So that makes it so a lot of your area is actually under your feet, and it can be a lot easier to initiate a turn, and you can roll a lot smoother that way. Yeah, fuse length and tail. Yeah. So with your front wing, most front wings inherently want to nose your board down. They want to kind of tilt forward like this. And obviously that's bad, we want to be balanced. And so your tail exists to correct for that. And what the tail does is it's actually like your front wing, but flipped upside down. And so it's going to produce lift in the downward direction when you move through the water. And your fuse length basically can shape your tail size by giving that tail a longer lever to act on. So the longer your fuse, the smaller tail you can have, and still have that tail be able to counteract your front wing and nose your board back up. Or you can run a shorter fuse and a larger tail and get the same effect. And there's a lot you can play with the balance on that. Yeah, so tail angle is a bit of, I think, a hotly debated topic. I've had a lot of people come in here and ask why we don't have shims. And I think that's part of that is because we know the general weight range for people. We know how our front wing likes to pitch down. And you can kind of really dial in your tail at a specific angle and have that work for most people with where our tracks are. And so what the tail angle does, usually these tails are pitched a few degrees this way. And what that does is help your tail produce a little bit more lift so it can counteract that nose down moment from the front wing a little bit better. So I guess a lot of people think about surface area as how much lift a foil is going to produce, which is kind of a misconception because like if I'm up and riding on a foil, I weigh 155 pounds. If I'm out of the water and riding level on a foil, that wing is giving me 155 pounds of lift plus gear. And unless I go to do a turn or I try to pump or something, that's not changing, no matter what size range I ride. But what it is kind of changing is the size of your foil dictates kind of how much angle you're going to need to produce that amount of lift. And so if I'm riding, say, our 775 and I'm going 10 miles an hour, maybe I need 1 degree tilted up to give myself that 155 pounds of lift. Where if I ride our 1100 at 10 miles an hour, I might be riding completely level because I still only need to produce 155 pounds of lift, but now I'm on a bigger wing. I'm trying to think of what I want to start. I'm definitely going to need a diagram. Yeah. So if you look at our plan form and you look at it side on and slice it, and then you look at that 2D cross section, that's what we call an airfoil. And so when you have an airfoil, you have a thickness, a camber, and that camber has a location. And so what camber is basically is if you draw an airfoil and we'll start with a symmetric airfoil, and then you look at kind of the center line from the leading edge to the trailing edge. That's what we call our camber line. And so on a symmetric airfoil, there is no camber. So that line is flat, there's no percentage of camber. If you start to distort that airfoil and bend it, you can see the camber coming in, and that line basically just gets a bow in it. So you can think of camber kind of as how much bow is in our airfoil. And that camber has a location where it's at a maximum. And that location has a pretty big effect on the pitch stability of our whole setup. So if you push it backwards towards the trailing edge of the foil, you can kind of lose your top end ability, and you can actually get a huge nose down moment at the higher speeds. Where if you kind of bring that camber location up towards the leading edge, you'll end up with a foil that performs a bit better at the top end and doesn't want to nose down so much when you get up to those really high speeds, which if you've ever ridden a foil that does that, it can be kind of terrifying, right? You're putting all of your weight on your back foot, you feel out of control. And so what the Helix actually does is it has kind of a moderately cambered airfoil profile with that camber more towards the front. So it tends to perform really well at the high speeds. You can push the top end really high, and it's still going to be very nice and stable at those high speeds. With thickness, you can kind of just scale the thickness. We scale it as a percentage of the chord. And so that chord is your leading edge to trailing edge length. And usually thicknesses kind of range from like the 9 to 15% range. And a thinner thickness can reduce your drag a little bit, but it tends to stall out really hard, where a larger percentage thickness, if you have a thicker airfoil, it'll stall a lot easier, but you also gain some drag. And so those thicker airfoils can sometimes have a lot lower top end, but they perform a little bit better at the low speeds. And then so structurally, why you would go thicker is if you have, say, a much higher aspect ratio foil, then you have a lot of your load farther out towards the wingtips compared to a smaller, surfier foil. And at the same time, your chord is decreasing in length. And so there's a huge amount of bending force at the base of that foil. And so what you a lot of times will do is you'll make this root section a little bit thicker on the foil. That way this center of your wing can handle a lot more of that load, and then you can thin it down as you travel towards the tips. So recently something that's come into play is twist through your wing. And so what happens is you have, just like you can have your planform at an angle of attack, you can also have your individual airfoil sections at different angles of attack through your wing. And so a lot of times what you'll do is you'll twist these sections as you move out towards the tips to help center your lift under your feet and to help the wing roll a little better, and also to get rid of what we call tip vortices, which account for a good percentage of your drag. And so if you really dial in the twist on these wings, it can help you unlock a lot more efficiency across your speed range.